So now we're going to get into the meat and the potatoes of calculus. All right. One of the great inventions of all human history is this thing here called the derivative. And the ideas that go on behind the derivative are just, they're everywhere. All right. Basically, if you guys are going to study anything that has to do with any kind of mathematics, any kind of science, any kind of computer science, um, anything at all, really, okay, you are going to be utilizing derivatives all the time. In fact, if you study physics, or many of you guys are going to take physics, what you should just remember is basically everything you're looking at is a derivative of something, right? Or it's an integral of something, which we'll get to later, right? But basically, that chemistry, uh, certain parts of biology, right? You're going to see this derivative all over the place. And here it is. Here's the derivative, okay, of a function f at a number a, denoted by, and here what I want to get, we call this is called f prime of a, okay? F prime. So f prime of a is f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a divided by h, provided the limit exists. Okay? So if that limit exists, then that's our derivative. Now here's the deal. Take a look at that. You should be thinking to yourself, I've seen that before. I've seen that many times before. I've seen things like that before. Okay? Because you have. All right? Because you have, right? The tangent line problem, basically what we'd say the slope of the tangent line, is a derivative. The instantaneous velocity is the derivative of the position. We'll get into that a lot more, okay? In addition to that, any rate of change, and we're going to talk about that a lot more inside of this video, any rate of change, okay, which we have another word for that, we call that a slope. Any rate of change is a derivative. That is what the derivative is. The derivative is a rate of change, okay? But specifically, it's an instantaneous rate of change, right? We had the secant lines, right, were our average rate of changes. The average velocity was an average rate of change, okay? And then we'll also see things like the slope of a line, like a straight line. That's also going to be an average rate of change too, okay? What we are talking about when we talk about the derivative is we're talking about an instantaneous rate of change, the rate of change at a point. Rate of change at a point, okay? And it goes back to that problem that we were talking about when we started talking about velocity, right? The problem with velocity is, or we were looking at average velocity, is that it's not actually the velocity that we're traveling at a specific moment. We can only, algebraically, we can only solve for velocity by taking our position at one place, subtracting the position at a starting place, and then dividing by how long it takes us to get there, okay? What this does is it solves the problem of how fast am I going at exactly this point, or at exactly this time. It solves the problem of what's the slope of this curve at exactly this point. So rather than us having to take 2 points, find a secant line, we can figure out what that slope is at exactly a particular point, okay? So when we talk about the derivative, right, when we talk about f prime, here's what I want you to always be thinking of. Rate of change, okay? Slope. Slope of the tangent line, an instantaneous rate of change, okay? It's that idea. It's exactly that idea that's going on when we work with derivatives, right? And we want to kind of like hone ourselves in on that's the idea that I want to get when I'm thinking about a derivative. These equations, this equation for the derivative, okay, it just displays that, right? This is the change in y divided by the change in x. Yes, just look at that. But we add the limit part to represent as we get closer and closer and closer to a particular value. Another way for us to write the derivative would be something along these lines. We could also write it as, right, the limit as x approaches a of f of x minus f of a all over x minus a. Okay? And again, that's just kind of like representing what happens, right, to this rate of change, okay, as x gets closer and closer to a. And finally, let me introduce some notation that what we'll use this for is we'll use it to do some more work especially when we work with the integrals, and we'll look at some things called differentials. All right. So I'm going to utilize this thing. It's a triangle, okay, and we're going to call this thing delta x. Now, what delta x is it's an increment. All right. We call that an increment, and what it basically is it's going to equal x2 minus x1, right? Okay. Generally, when we use delta x, it's going to be of a fixed size, all right? So it's a fixed size, so we might talk about it delta x equals 0.5 or delta x equals 1, right? And what that means is that the difference between any two x's is going to equal 1, okay? Then we'll have a delta y, and delta y also is going to equal y2 minus y1, okay? Or f of x2 minus f of x1. Right? We don't call that an increment because it's going to be dependent upon what x2 and x1 are generally. Okay? So, an average rate of change, maybe we call this our delta, right? Okay? Often called delta, right? This is called delta. It's called delta, right? That's what a triangle is in Greek. The rate of change is going to look like delta y divided by delta x. Change in y over change in x. Okay? And we even call that our slope. So our derivative, right, f prime of x is then going to equal delta y, the limit, as delta x goes to 0. So as that increment goes to 0 of delta y over delta x. Okay? And so you want to sit down and be like, oh, okay, that's basically the same thing. We might write this as, right, the limit as x1 approaches x2 of f of x2 minus f of x1 divided by x2 minus x1. And that's just some notation that we're going to see for instantaneous rates of change and for derivatives, okay? So inside of this section, there are some application problems on how we see things, especially like inside of business and things like that. I'm going to assign those as readings. But I want you to watch this first and then do those readings and see if you can kind of like make sense of what they're talking about. What does the derivative mean in this particular circumstance? All right. That completes this mini section on the derivative. 2.1, we're going to get into the derivative even more. In fact, the next 3 weeks, 4 weeks, 5 weeks, well, the next 15, 20 lessons that we're going to get into are all going to be about the derivative.